Alright, so today we're gonna learn lesson number 7, which is application of magnetic field and force, and at the same time, Lenz's law. Lenz's law, if it's go the way as I planned, it's gonna be a little longer than application of magnetic field and forces, so have that in your mind. Before we getting into it, let's do a little bit of a homework check from lesson number 6. I picked specifically question number 4 because I found that the previous video kind of cut how I use my left hand or right hand rule. So I'm going to apply this a little bit better. So when it comes to this question number 4, an alpha particle enters a perpendicular 75.0 millitesla magnetic field at a speed of 3.90 10 to the 5 meter per second. Is this motion clockwise or counterclockwise? That's a part A question. And part B, what is the radius of the curvature? So it is asking about the value of R instead of value of V. So I think it's a good connection point. First thing first, alpha particle. Those are positively charged particle, which means you need to use right hand rule. So instead of left hand, I'm going to use my right hand and thumb represent where the this V P direction is, which is thumb to the side. Now forefinger, I have a two choice. Basically, is it going into the page or out of the page? Right now it's out of the page. So if I, which is a little hard to do, if I place my thumb and forefinger like that, my palm direction is in fact not literally in here as soon as we enter. My force direction is going down the page. Now remember folks, in a moving charge and external magnetic field, you are experiencing a circular motion. So it is a good idea to predict the motion that goes like that. It is actually, imagine making a circle, now like this, assuming that this magnetic field is continuous. At this point, you need to also understand that my force direction is going towards this center of the circle. And the question is basically asking about this R value. So first thing first, is the motion clockwise or counterclockwise? Well, we have to use a right-handed rule because it's positively charged subatomic particle. So it is. Oops. Is it? Oh yeah, it is clockwise. Going clockwise. So A is done. When it comes to B, what is the radius of curvature? Let's actually write down some of the clue first. We know that magnetic field amount is 0.0750 Tesla. We know the value. We also know my speed, 39000. I kind of, you can put 10 to the power of 5 if you want. It's 1, 2, 3, 4, 5. Sorry, one more. Let me double check. 1, 2, 3, 4, 5 meter per second. It's not that long number. And we're trying to find R. In fact, we know other two clues. For instance, we know Q is 1.60 10 to the power of negative 19, but double that, so 3.20 10 to the power of negative 19 C. In fact, it is positive, but who cares about the direction right now? We already found out the direction using a right-handed rule in this situation. So Q is that. And we're trying to, oh, and mass is also given. When it comes to mass, please refer your Physics 30 data booklet or formula sheet. I don't have it right now, so I'm just gonna put it up on the screen if that's okay. there you go. As you may know, the alpha particle's mass is given in your data booklet as 6.65 10 to the power of negative 27. Using these, I don't recommend you to memorize the whole formula and derivation of it. I rather highly encourage you to calculate and derive on spot. And that involves some theory. My net force, which is centripetal force, that is equal to my magnetic force in here, because that's the only force that exists in the system. What I need to do now is mass and acceleration, which I can easily put mv squared r, and this can be qbv. And we can cancel one of the velocity out. Isolate for r situation. R is equal to, therefore, mv over qb. Now we can basically punch every single number in. My value that I need to find r has mass on the top 6.65 10 to the power of negative 27 kilo. Velocity or speed in this case 39000. Oh, sorry, 0000. 390,000 and over q 3.20 10 to the power of negative 19 and b 6.65. Oops. Yeah, B I put, oh, magnetic field, which is over here, 0.0750 Tesla. And my basic unit for R is meter. So let's punch these numbers in. You should have, and I'm going to put rounded answer, which is 3 significant digits, 0.108 Tesla. Oops, sorry, meter, which is radius basic unit. And that's quite reasonable radius. In fact, if you think about it, it's about 10.8 centimeter. So that's how you solve some of those moving charge in an external magnetic field. What can I find in terms of force, or what kind of clue I can find using the force concept? This is the one. Today's lesson involves quite some application of electromagnetism. It does involve force and field. So let's talk about one of them, right? Speaker. Especially if you have a really bad speaker, or if you have any type of your headphones or any type of a Beat by Dre kind of big type of a headphone, it is actually recommended to use those as a little bit of demonstration in your house. Just what you need to do is connect it to your iPhone, iPod, or any type of MP3 player, and then you just need to crank it up to maximum volume. Instead of bringing it to your eardrum, what you need to do is put on your hand on it. Because here's the thing. The way that electromagnetism works for speaker is, number one, we use, of course, electric energy, but electric energy will basically make or transform into mechanical energy. And mechanical energy, yeah, you can see everything. And mechanical energy will basically make you to use a concept of force. Why force is involved? Because we have a velocity and acceleration because of that. Basically what this force does is, it's gonna vibrate. The reason we can hear any of a sound in real life situation is because whatever things that I'm saying it to you right now, you can hear it through your laptop or electronic devices, whatever you want to call it. You can hear my voice because the air molecules vibrate, and this wave energy make a little bit of a mechanical energy conversion, and from there you can hear it because your eardrum will basically vibrate, and that vibration give a little electric energy to your neuron, and that's a biology 30 concept that you're going to learn. However, long story short, the current, I'm going to highlight some of the portion, the current carrying wire are the one that is involved in this entire system. And it's external signal, we like to call it. When it comes to electron, think about it, negative electrode to positive electrode, it's going to go up in this situation and down, 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 down. So if you actually think about it, this is left hand rule number 2, which is 4 fingers in front of you. And on my thumb, which is directing towards west, that represents my north. The other side represents my south, because my magnetic field inside should go like this. If you look at just this diagram, north and north, there's a repelling occurring, which means they're gonna move away. So technically this entire cone trying to move away from it. But I can easily alter this electrode when it comes to an AC current system. AC represents alternating current. So let's go through that concept one by one. First thing first, the currents come from external signal. It goes around the coil and magnetize this region, which I mentioned that, left-hand rule number 2. And by repelling, and I can technically change into positive and negative using alternating current, it can attract to each other too. Right now it's repelling. By doing the repelling and attraction, you can actually create a mechanical energy, and that will create the force, and that will vibrate. So, the thing that I'm going to highlight in this situation is repelling and attraction of the fixed magnet that you see on this area over here. You're actually creating some kind of mechanical energy or force in this case because it vibrates. And this vibration basically creates a sound wave, and that's how we can hear things. It can be amplified, and whenever you have amplified sound, you're actually going to have a lot of vibration, just for the heads up. Number 2, any type of lifting electromagnets. I believe this is a little bit located high, so I'm going to mention to that level. Number 2, electromagnet. When it comes to this, think about it like a construction site, or technically it's more of a car recycling field, something like that. Basically, what you see over here, the disc, that can become magnet. And the way that it becomes magnet, of course, like what I mentioned, left-hand rule number 2 uses a lot for this mechanism. Let's talk about that in here a little bit. Remember, short side is negative, long side is positive. So, if I draw the circuit, that's the way. And if you think about it, it's going to go behind and left, 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 goes up, and then when it comes to go around, just follow your diagram. You will find that one goes around on the left, one goes around as a right. Now, if that happened, let's look at my left hand rule. 4 fingers in front of you. So my thumb is actually facing up, which is north over here, south over here. If I look at the other situation, 4 fingers in front of you, and it's thumbs down situation, so north down, left, and then above direction is actually south. So once I look at this situation, I actually created what I like to call my temporary magnet. And when it comes to my any type of object that you try to lift, these are unmagnetized material. So the domain around these will be quite random, except for this certain region, it's going to go towards the S. When it comes the other way around, it's going to be the north. Another random area will have random domain. But in any cases, this is how things are attracted. There should be no repelling occur. So attraction only. So if I highlight some of those sections, this is what I like to highlight. First thing first, lifting an electromagnetized magnet is basically composed of two solenoids. So please highlight that two solenoid that have wires that is opposite direction, wrapped in opposite direction. So one side will be south, another side will be north. Vice versa can be possible. When the current flows, those poles create the end of the solenoid, south or north, like what I draw in here, and that basically create a temporary horseshoe magnets. And unmagnetized materials domain will get induced, and from there you can actually lift. And lifting part will be twice of the strength because you have two solenoids. That's my second technology I like to go through. Any type of alarm, especially old style electric bell or fire alarm, we use, again, like what you see on the previous example, two solenoids. And it has a soft core of the metal, but that's more filler part situation. The magnet induces the opposite pole, like what we talked about, south and north situation. If you like to go through, let's give it a shot. Negative is basically going around like this. So, one of them will face down, one of them will face up. Face down situation, north, my thumb pointing on the west. The one that go above, north on the right, south on the left. Which is very similar as what you see up. Now what happened is, because of these, you're going to have attraction. Once you have attraction going on, now what happens is there will be some kind of a force. They tend to go close together. And what happens is by moving this, there's a little torque is what we call the circular force motion and momentum. The torque will make this hit. But once it hit, then you may notice that there is a little contact screw. You're going to temporarily disconnect and break the circuit. So here's what I also want to point it out as a highlight. When the armature, which is this portion, movable section, you can think of it that way. Armature move, then the contact screw break the circuit, and there will be no flow. So it hit the bell, then after that, it's gonna basically break the circuit. Once that happens, it's going to come back, it's going to connect the flow again, and it's hit again and release, hit, release, hit, release, hit, release, and it's going to repeat. So the whole cycle will be repeat. This is one of the reasons why when it comes to the frequency of those, it's actually quite a lot of frequency, and it's going to be loud too because sound wave will be amplified. That's basically what I want to say about electric bell. So think about these 1, 2, 3 technology. when it comes to Ford technology, motor, call it motor effect, you need to think about a few sections. And to be fair, this plays more huge role when it comes to a Science 30 diploma instead of Physics 30 diploma. But in any case, first thing first, there's a DC and AC. DC is direct current and AC is alternating current. Alternating current is way better technology because DC, imagine direct current is one direction. Alternate current is multi-direction. But in any case, long story short, let's look at the motor effect. So, when a current carrying armature is placed with the magnetic field, the location where the current is perpendicular to the magnetic field will experience magnetic force. So if you really want to know Physics 30 components of it, this is what you need to remember. We're talking about perpendicular placement between the wire and the magnetic field. So basically this use left hand rule number 3 or right hand rule number 3. And let's actually apply to each of the situations. First thing first, when it comes to motor, you need to understand that it's always electrical energy as a start and mechanical energy as going to. If it's other way around, that's a power generator. Again, Science 30 talk about this more. So if I talk about electron movement, negative to positive. So first thing first, third rule, north to south is basically going left to right. That is my magnetic field direction. Now my thumb, which is going almost into the page edge, can bring my palm going upward. On the other hand, if I look at my left wire situation, it's more like out of the page edge, and then left to right, that direction doesn't change, so my forefingers are directing right, and my palm is forcing it downside. And if that happens, if you look at this entire wire situation, it's actually gonna make everything, again, it's a use of the word torque, which we don't learn in high school, but think about it as a circular motion related physics term. The torque basically will create the whole mechanical motion as counterclockwise in this situation. There's one thing that you need to understand. And that's the part where if you look at the angle 0, 180, 90, and 270, I'm gonna highlight